Mathematically, linear regression can be represented with the equation here, in which y is the prediction value or dependent variable. B0 represents the intercept. B1, B2, all the way through Bn represents the individual coefficients, and the x's represent the independent variables. The most interesting part of the equation is the coefficients themselves, because they tell us how each individual variable affects the dependent variable. To make use of a regression model, certain assumptions must be made beforehand. In this video, we'll be discussing simple and multiple linear regression. Linear regression is one of the most common methods of representing or predicting a dependent variable from one or more independent variables along a continuous plane. In the picture here, the red line represents the model or how it is fit to the data, with each blue dot representing a single data point. As you can see, the red line is the closest possible way in which we can represent each individual data point along a two-dimensional plane. The model works by attempting to minimize the sum of squared differences between the predicted value and the original data points. In the picture here, the red arrows represent the residuals or the vertical errors between the actual data point and the predicted values. But the model itself does not attempt to minimize the sum of individual residuals, but rather the sum of their squares. This effectively penalizes data points which are very far away, the first of which is homoscedasticity. Homoscedasticity refers to the error or spread of the data across the independent variables. The graph here on the left is what we're aiming for, in which the error or spread is constant across various independent variables. On the right, however, we see a fan shape in which our errors, or our model on the left, would be highly accurate with very little spread between the predicted value and the actual values. But on the high end of our independent variable, we would have much larger errors or spread between the predicted value and the actual values. This brings us to the more general topic of normally distributed residuals, which is another assumption that should be made before interpreting or making claims based off of our linear model. When analyzing the residuals, no shape should be apparent, and this is what we see in the left-hand side. This means that our model is interpreting the data that is to be interpreted, and all the error that remains is true randomness within the data set. On the right, however, we see a very apparent shape or trend. At the very low end, the errors are, the residuals themselves are negative. It then shifts to being positive, and then back down to negative. This means that another model or another method may be better fit for this data, and limited claims should be made from this data set. We will now build on these concepts by showing how easily they can be implemented within Excel. After this, we'll conduct similar analysis within Python. In Excel, it's important to ensure that we have the data analysis toolkit already installed. To ensure it's installed, go to Tools, Excel Add-ins, and you should see Analysis Toolpack. Make sure that's clicked. Here, we'll be doing a simple regression model with only one independent variable, square feet, and one dependent variable, price. First, let's visualize the data. This can be done by selecting the data, insert, scatter, and here we are. As we can see, it appears like there's a pretty linear relationship between the two variables, which is good. We can add a trend line here. And as we can see, the data does appear to be very linear. Notice that the trend line does not continue past our minimum and maximum values with regards to the independent variables. Now, while this may seem annoying, Excel is actually helping us because we should be very hesitant to make claims or predictions for data points that fall outside of this range because we do not have any historical data to base that off of. Now, let's go forward with the actual regression. We can do this by going to Data, Data Analysis, Regression. Here, the two most important inputs that we have to enter are the Y's and the X range. We can input the Y range by selecting it, and here we have price selected. We'll do the same with the X variable or variables, square feet. Here we see our regression output. The R squared tells us how much of the Y variable can be explained by the X variables. Here, 93% of it can be explained, which is very good. Let's bring our attention down here. This tells us the intercept and X variable 1, which refers to square feet. The coefficients, if you think back to the mathematical equation we looked at earlier in the video, these coefficients will be inserted into that equation. The p-value tells us how likely it is that we would have gotten values as extreme as these if there truly was no relationship between the variables. A p-value of 0.0001 for square feet implies that it's almost impossible for this to have happened by chance, specifically this relationship. Now that we have our coefficients in place, we're ready to represent our linear regression equation. The equation is typically written in the following form: y equals, we have our intercept coefficient here, and that is 851.59, plus, and then we have the x variable 1 referring to square feet, and that has a coefficient of 1.05. So 1.05 times x, in which x is the square feet. Now that we have our equation here, we're ready to make a prediction about this new value. A new apartment or house with a square footage of 1,500. So we plug 1,500 into this equation here. And we get a prediction of 2,426.59. Let's look back to our chart to see how that looks. At the 1,500 mark, our equation predicts that we will have a price of just under $2,500. Similar example, but this time we'll be using multiple independent variables, bathrooms, bedrooms, and square footage to predict our price variable. We'll go through similar steps. So, data analysis, regression. We select our single y variable. And this time, we're going to select all three of our x variables. Because I have multiple variables this time, I'm going to include the labels, and I'll make sure I have the labels on the y as well, just for consistency. And we'll click this box, labels, and that'll help us distinguish them within the regression output. Here we are, and it seems like we have pretty similar results to last time, but this time we have coefficients, standard errors, and p-values, as well as confidence intervals for all of our variables. It seems like bathrooms has a negative coefficient, and it seems like both bathrooms and bedrooms are related very weakly to our price variable because with a high p-value, that means they are very likely to have occurred simply by chance, even if there was no relationship between the two. This is supported when looking at our confidence intervals because 0 is within the range of the lower 95 bracket and the upper 95 bracket for both bathrooms and bedrooms. That means that 0 is a very reasonable actual population value. While it may not be the sample coefficient, it could be the population coefficient, in which case it would have no relation to price. We're going to go through similar steps to predict an apartment with 2 bathrooms, 2 bedrooms, and 1,500 square feet. We represent our equation first, y equals 2x1 plus 2x2 plus 1,500 of our third x variable, x3. We can calculate that below. We're going to go through similar steps, but this time we'll be looking at a data set with multiple independent variables in order to predict a single dependent variable price. We'll go through the same steps: data, data analysis, regression. We'll select the entire y range, including the label, and we'll select the entire x range as well with the labels. We'll make sure our labels is checked, and the reason we're doing this is so that we can distinguish the variables once they're put into our output. Here, we see very similar output as we did on the last sheet with only one variable, but instead of using one, we have 1, 2, 3 variables here, and that means 3 x coefficients. You may notice that both bathrooms and bedrooms have very high p-values. This means it is likely that we would have gotten a result as extreme as the one we saw here had there been no true correlation between bathrooms and bedrooms within the actual population. Our sample coefficient certainly has value that is not equal to 0, but because 0 falls within our lower 95 or upper 95 bracket here, so because 0 is between negative 807 and positive 675, and 0 is between negative 467 and positive 639, we cannot be confident that there is any relationship between bathrooms and price or bedrooms and price because the true coefficient could very well be 0, in which case there is no relation. However, we still have a pretty strong p-value for square footage, implying that it is a good predictor of our price variable. While it is difficult to visualize three variables at once, as we did on the previous sheet when we were only looking at square footage, we can still go through the same steps in calculating or predicting a new data point. Here we have 2 bathrooms, 2 bedrooms, and 1,500 square feet. If we were to put that into our linear regression equation, it would go something like this: y equals 2 times, and then the coefficient for bathrooms, which is negative 65, .7, plus 2 times the coefficient for bedrooms, which is 85.84, and 1,500 times the coefficient for square feet. And we'll notice that the coefficient is similar, but not exactly the same as it was in our previous data set. When we actually go through the process of plugging those numbers in, and we can't forget our intercept of 879. This time, we get a prediction of 2,448, which is fairly close to our last prediction. Now we'll conduct similar analysis, but this time within Python. We'll import the same libraries that we did with the KNN video, pandas, and NumPy, but this time, instead of importing k-nearest regressor or k-nearest classifier, we'll be importing linear regression. Because our data set is so large, we've changed the options so that 100 columns can fit at once. Additionally, we imported mean squared error, which is one of the metrics from the sklearn library. This will be used later on as we evaluate our model. After reading in the dataset, we can see that we have roughly 80 variables, and we'll be attempting to predict sale price. Additionally, we see that we have some null values, and we have some variables that are non-numerical, such as functional or kitchen quality. While there are more sophisticated methods that we can do that will allow us to implement some of those variables into our model, for now, we're just going to go ahead and use the simplest and most complete variables: lot area, pool area, overall quality, overall condition, garage cars, and garage area. We'll be using these to predict the sale price. After filtering down our dataset to just these variables, we're ready to split the dataset into a train and test component. In the later video, we'll be covering cross-validation, which is a more sophisticated method of splitting the dataset into the train and test components. We will instantiate our model here by calling the linear regression function, and we'll assign it to model. Then we'll fit the model. First, we'll input our x variables, the train x variables. Then we will be fitting it to our output, the y variable of the train dataset. Now we fit the model. After having done that, the coefficients will have been saved as an attribute of the model variable, model.coefficient. There should be 6 of them because we have 6 independent variables. We print each of them here: lot area, pull area, overall quality, overall condition, garage cards, and garage area. It seems that overall quality has the largest impact on our output sale price per unit of input. Additionally, just as the coefficients are saved to the attribute model.coef, the intercept is saved to the attribute model.intercept. Now that we have our intercept and our coefficients, just as we did in Excel, we can put these together to form our regression equation, which we see here. We could use this to make manual predictions, but the scikit-learn library has some functions in place that will make this much easier and easier to implement. First, we'll evaluate the overall model performance. The R squared tells us how much of the variability in Y can be attributed to the variability within the independent or X variables. Here, that value comes out to roughly 71%. Now that we have our model and we have some idea of how it works, we can make predictions with it by calling model.predict. This time, we'll be predicting from the dataset that has not been touched yet. That would be the test dataset. And we'll be making predictions based off of the X variables or the independent variables. And we'll be saving that to predictions. Then we'll be assigning those predictions to a new column within the test dataset. Now that we've made our predictions, we're ready to see our error metrics. This is a pretty large concept and it's something we're going to dive deeper into in later videos. But for now, we'll focus on the mean squared error and the root mean squared error because this is what linear regression is attempting to minimize behind the scenes. We imported the mean squared error function at the beginning, but this could be done with simple algebraic functions. We input the Y variable of the test dataset as well as our predictions. So we'll be looking at the difference between the actual value and our prediction, calculating the mean squared difference, and calculating the square root of that. Here we see our values, and it tells us that a typical error might be in the range of around 45,000. Surely some will be much larger and some will be smaller. We'll create a new column, this time for the prediction error. We'll calculate the absolute value of the difference between the actual value and our prediction. And we'll represent that as a percentage as well by taking the error and dividing it by the actual sale price. Let's visualize those errors here. We'll call the box plot method from the pandas library. Typically, I like to use pyplot or seaborn to create visualizations within Python, but boxplot is one of the ones that's easy to implement within pandas. You simply input the column you want to create a boxplot on. Here it's prediction error and prediction error percentage. We see that just as our root mean squared error told us above, a typical error might be in the range of under 50,000, which is what we see here. This is being pulled up by a few outliers on the high range. So there are a few houses in which our model was not very accurate on, but it seems like most of the predictions were within, let's say, about 10,000 to 40,000. When we look at that as a percentage of the actual value, we see pretty similar results. There's a few outliers on the high end, but most of our predictions fall within, I'd say, 10 to 25% error, which is pretty good, considering we only used a few variables and we did not use very sophisticated methods to select the variables. Here, we'll discuss some of the advantages and the disadvantages that linear regression can offer. As we saw, some of the advantages are that it's very simple, intuitive, and easy to implement. It can perform well on a wide variety of problems across very different domains, including business or science. Additionally, it does not require hyperparameter tuning like the k-nearest neighbors algorithm did in the previous video, or, as we'll see in some of the following videos, random forest regressors or random forest classifiers, which will require much more extensive hyperparameter tuning. It is ideal when you know there is a linear relationship between the input variables and the output variables, but usually this is not the case. Additionally, linear regression is highly explainable. This is a concept that can apply to any of the models we'll see in other videos. There is generally a trade-off between accuracy and explainability. Accurate models, which may be very difficult to interpret or communicate, are called black box algorithms. On the opposite end of the spectrum, we have linear regression, which is considered a white box algorithm because we can understand how it is operating on a fundamental level. Specifically, we can understand and communicate the specific coefficients within the algorithm. One of the reasons regression is so popular is because of this explainability, but there is not as much of a drop-off in accuracy as one might expect for a model that is so easy to interpret and explain. This is why regression is so popular. Some of the disadvantages that we may have touched on earlier is that linear regression relies on assumptions that are not always met. Additionally, linear regression assumes independence of the input variables. One example I like to use to communicate this is imagine a similar problem that we were working on recently, and imagine that distance to the beach is one of the variables, as well as size of the balcony. One would expect that sales price would increase as the balconies get larger or as the distance to the beach gets smaller. But our model would fail to understand that a balcony would add much more value if it is near the beach. Specifically, if a balcony increased by 100 square feet and that building was close to the beach, you would expect a larger increase in sales price than if the balcony increased by 100 square feet and it was overlooking a balcony or not near the beach. This is something that linear regression would fail to identify, but another algorithm, such as a deep learning algorithm or even a tree-based algorithm, may be able to pick up on the subtlety. Additionally, it is susceptible to outliers, and it always assumes that there is a linear relationship between the variables. This goes back to the assumptions that must be made before making claims based on a regression output.